from Rijksuniversiteit Groningen, and he will speak about scaling relationship between the copositive cone and hierarchy of semidefinite approximations.
Okay, thanks. So, hello everyone. So said I'll be talking about some relationships that exist between the copositive cone and the semi-definite cone. And I'm cheating a little bit here because actually it's a relationship that will exist between the copositive cone and the cone of sum of squares, polynomials, which is in some way equivalent to semi-definite programming. So yeah, as promised by Peter Dixon, I'll be talking about the copositive cone today. So the work I'll be presenting today is based on two papers that I wrote with these three people. So Peter Dixon, who you saw yesterday, who's here, Miriam Duur, which is my supervisor, and Ronald Hildebrand, who works in France at the University of Grenoble. So yeah, as said, I'll be talking about the copositive cone. Granted, I won't be going into details on the copositive cone. I actually won't even be using any particular properties from the copositive cone in this talk, but just to get an idea of what this is. Well, it was introduced yesterday, so it's these matrices, symmetric matrices, for which this quadratic product here, x transpose AX, is non-negative. So it's similar to semi-definite, the semi-definite cone, except that these x's have to be non-negative. So the reason that we're interested in these types of cones, or people have become interested recently in these types of cones, is because it allows us to translate all sort of NP-hard problems as mostly linear optimization problems over the copositive cone. If you've ever attended a talk about copositive programming, then you will probably have seen this example before, which is the example by Sam Buehrer, which says that if you have quadratic mixed integer programming problems, so you have a quadratic objective function, a bunch of linear constraints, and then a few of these variables will be binary, then this problem can be formulated as a completely positive program, and the completely positive cone is the dual of the copositive cone. And a bunch of these tricks, by the way, in general for the copositive cone are very similar to tricks that you would use for semi-definite programming. So one of the things that's being used here is this here you would write as the inner product of Q and XX transpose, and you replace the XX transpose with a giant matrix X, and then you have an extra constraint which says that X is equal to XX transpose, and then you relax this, and then a type of Schur complement happens, and then you get this big matrix with this X here and then X transpose there, X, and a 1 here that has to be well, not semi-definite in this case, but here completely positive. Okay, so another good example is this one by de Klerk and Pesechnik for the clique number. And here really you only have one variable, and your only constraint is that some matrix here has to be in the copositive cone. And this matrix here is lambda times the identity plus the adjacency matrix minus the all ones. And considering that this is, one variable and this is your only constraint, that sort of already implies the complexity of checking this membership, because checking this is co-MP complete, which is a result by Mouti and Kabat. So this is for the copositive cone. Surprisingly, when I started my PhD about 2.5 years ago, I asked, so that must mean that the completely positive cone, the dual, must also be an NP-hard problem, but apparently at that time that was still an open problem. At least there was no actual proof for this. So that is something I did together with Peter Dickinson. So also for the dual, this is a hard problem, which was expected but not known. In fact, I guess it should be possible in general to show something that if for a certain set or a certain cone, checking whether it's in there is in a certain complexity class, you would expect that that is also true for the dual. I'm guessing this should be possible to prove in general. Maybe there's even some results in that direction, but I don't know that much about complexity, so maybe there's someone else that knows something about that. So as we did those results, we also got some extra results for free, which sort of implies some extra hardness on these on this membership problem. So we have here the weak membership problem. So here we have some sets sk delta, and we have here some cone or set k as a subset of Rn. And then these sk deltas are basically, this is set k plus all the points that are at a distance delta from, or at most delta from k. So this is like an outer approximation, and likewise this is an inner approximation in that sense. And then the weak membership problem is just to decide whether either you're in that outer approximation or you're not inside the inner approximation. And then to summarize, we got this result which shows that both the weak and the strong membership problems are actually NP-hard problems for the copositive cone. So this is really quite a hard problem. So one of the things that you do then is you find approximations. So one of the nice things is, because everything else is nicely linear and stuff, so we know how to deal with that for the most part. So if you have some approximation for the copositive cone that is tractable, you can just plug that in there and you immediately get approximations for all these types of problems that can be translated as copositive programs. Well, the one that I'll be focusing on is an approximation hierarchy that was introduced by Pablo Perillo. So we have these KR cones. So R here is the level of the hierarchy, and those are just all the matrices. So that here we have this quadratic term again, x transpose AX, and then you multiply it with the sum of the xi to the power R, and that has to be sum of squares. And then we also have here squares on these variables, which is basically just to replace the non-negativity constraints of the axis. And as said, the fact that this thing is sum of squares can be checked by a semi-definite programming, which is a sort of a, well, an artifact of the fact that semi-definite is the same as saying that you can write a matrix as the product of BB transpose. In fact, there's quite a lot of redundancy in those giant matrices that you would construct for the semi-definite programs to determine the sum of squaredness. So for the K1 cone, you can actually show that it's enough to solve this set of constraints. So you have a bunch of linear constraints, and then here these semi-definite constraints. So you construct n of these matrices, which are just size n by n, and then you have these n semi-definite constraints. And it says here if and only if. So x is in K1 if this all holds. But if I'm correct, Perillo only showed the if direction in his thesis, and the other direction I think is proven in the paper by Bomse and de Klerk. Has then some properties. So I said R is the level, so K0 is a subset, etc. If you take the union of these things and then the closure, you get the copositive cone back. The K0 turns out is equal to the semi-definite cone plus the non-negative. So in a sense, the semi-definite cone is of course already a relaxation of the copositive cone. So in a sense, you could see it as these K cones sort of connect the semi-definite cone all the way to the copositive cone. And then we have this property here, which says that the copositive cone turns out to be equal to the K0 for n at most 4. So then the question, of course, is immediately, well, what happens then for n equals 5? And, well, for n equals 5, they're not equal. And this would be a counterexample. So this is all 1s, except here the off-diagonal are minus 1s, and there's a minus 1 there. And this matrix is called the Horn matrix, and it is, as it turns out, an extreme ray of the 5 by 5 copositive cone. So it's in the copositive cone, but it's not in K0. So then the next thing, of course, that you could do is you increase R by 1, and what happens then? So what happens if you take R bigger or equal to 0? In fact, a question that had been asked is what would be the minimum n for which this is no longer the case? And some of the intuition behind why this would make sense is certain classes of extreme rays that turned out to be inside of the K1 cone. In fact, we had this little theorem ourselves. So if you have matrices with just minus 1s and 1s, then that matrix has to be in K1 for any dimension. And the Horn matrix, which is an extreme ray, is in this class of matrices, of course. Proof of this is very simple. So this is your certificate, and then it's not that hard to see that all of this works out. Okay, so next slide I'll have some small notation things. So I'm assuming that everyone here knows what a permutation is, but just so we're all on the same page. When I talk about a permutation of a matrix A, I just mean this guy here, PA, P transpose, so your rows and your columns get permuted in the same way. So you're not allowed to permute those differently. And of course, relabeling variables doesn't change whether a polynomial is sum of squares or not, or whether it's copositive or not. So these things are all closed under permutations. Likewise, we have scalings of a matrix A, which is DAD, for some D, which is diagonal, with the diagonal being strictly positive. Well, so the K0 is equal to the semi-definite cone plus the non-negative cone, so obviously that's going to be closed under scaling. As it turns out, the copositive cone is also closed under scaling. For the rest of them, though, as it turns out, they are not closed under scaling. So since the copositive cone is closed under scaling with respect to our earlier question, that's going to give us some problems. Because apparently we can always scale matrices out of every possible cone. So we have this theorem here, which says that for any matrix X in the copositive cone, not in K0, for any R strictly greater than 0, there's always a scaling such that the scaling is no longer in that KR. So as soon as you give me a scaling, whether you pick K a million or even bigger, you can always scale it out. So there's always some difference with the copositive cone. We proved this by this sort of equivalent lemma, which says that all the matrix X, for which all scalings are in KR, is exactly equal to the K0 cone. And the proof of this is quite simple, as it turns out. So this K0 is a subset of this, because it's closed under scaling. Then for the other direction, we just pick an X in KR for some strictly positive R. And if it's in KR, that means this polynomial here has to be sum of squares by the definition of those KR, and these DI, DJs turn up because of the scaling. Then we apply a substitution here, so we would get here Zi squared times Zj squared, and here we would get Zj squared over Di, which has to be sum of squares. And in particular, this then has to hold for every possible scaling. So in particular, we could just choose d1 equal to 1, and then we let everything else go to infinity. And because the cone of sum of squares polynomials is closed, this has to hold for the limit. So we get actually that this guy here has to be sum of squares, which means it can be written like this. And then here now, notice if you pick the z1 equal to 0, then this whole thing becomes 0 regardless of how you pick anything else. So because this is non-negative and all these terms are non-negative, every term has to be 0. So apparently we can factor out one of these z1s. And because it's a sum of squares, they come out as squares. So we get z1 squared multiplied by something has to be sum of squares, so that something must then be sum of squares. So that's something being this. And you just repeat this argument r minus 1 times, and you get exactly the definition of the K0 back.
More generally true, right? If you have something which is non-negative but not a sum of squares, you can do a scaling such that when you multiply by any power of sum of xi squared to the r, it won't be a sum of squares, right? Is in a paper of Resnick, I don't know if you've seen it, it's called Absence of Uniform Denominator. Right?
Was that the paper of Powers and Resnick?
I'm sorry?
Is that the paper of Powers and Resnick?
It's a paper of just Resnick.
Oh, I don't think I've seen it, sorry.
Is a trick to make any level of the hierarchy fail for any polynomial, not just the ones coming from the copositive.
Okay.
It's silly.
Okay, I didn't know that existed. Okay, so this is sort of the bad news of this talk, and then there is also some good news, albeit for a slightly less general case. So this is for the...
I mean, this isn't really, these are inner approximation hierarchies. So what you really want, what you really like is to make it bigger. So you'd like us to find a scaling D so that DAD is in the hierarchy.
Right, yeah.
For the completely positive cone, they're outer approximations. So the tightening makes more sense than for the copositive cone.
Yeah, no, I agree. So, I mean, that's what we're going to do next. So.
Oh, okay.
Well, I mean, for a very small case, but yes, it does make. But I mean, this question was still there, so I mean, this sort of solves that question. Right, so we're going to the 5 by 5 case here. So this started off with some results by Hildebrand. We showed that, so he introduced these S theta matrices, which turned out to be extreme rays of the 5 by 5 copositive cone. So you don't have to remember any of this for the purpose of this talk right now, but if you're going to remember anything, just remember that there were ones on the diagonal here. So in this paper he had this result, which is that if you have some A, which is a 5 by 5 copositive matrix, then either it has to be in K0 or it's in the orbit of one of these S theta matrices. So this really characterizes all the extreme rays for the 5 by 5 case, which up until then was not known. Okay, so yeah, either you're in K0 here or you're in this guy here. So in a sense, if you would know where these S theta matrices live, you maybe get some idea of where the rest of this cone lives. So what we then found was that these S theta matrices were in K1. The proof being very similar to before. So you have these LMIs for the K1 that you can just, so you give a certificate and you just check that everything holds. And then we also have another result here, which says that if you have a copositive cone, not in K0, 5 by 5, then you can always write it as the sum of R plus N, where N is a non-negative matrix with zeros on the diagonal, and R is some matrix in the orbit of one of these S theta matrices. So if we now combine these two things, that these S thetas are in K1 and this result here, we can actually do some things. That is, we just pick an X in the copositive cone, not in K0, and then we assume that there is a 0 on the diagonal somewhere. Without loss of generality, we can just pick it as the X11 element. Then you can decompose it like this. So you have here some non-negative matrix, and here you have some 4 by 4 matrix which is copositive, so that has to be in K0. So this whole matrix has to be in K0, which, you know, we already decided we weren't. So now we just assume that this diagonal is strictly positive, and then, well, by this theorem we can write it as the sum of these two matrices, so an orbit of these S theta matrices and a non-negative with zeros on the diagonal. And then the only problem really is, so this is in K0, this guy here is in K1, but K1 is not closed under scaling, so we just multiply left and right by the inverse of this scaling. So now we do get something here that's in K1, and we get something here that is in K0, so the sum has to be in K1. Of course, then you don't know the scaling yet, but because this guy has zeros on the diagonal, and this guy had ones on the diagonal, this is apparently exactly the scaling such that for X you get all ones, or at least for that scaling you get all ones on the diagonal. So now we have a way of checking copositivity for the 5 by 5 by just scaling in this way and then checking whether you're in K1 or not. I think I'll just I can. So for this result here, I can't show you exactly where this comes from, but I can give you an idea of how this was made. So this is from a thesis by Baumert from quite a while ago, and it has to do with irreducibility of certain matrices. So irreducibility, so these ij's here are just zero matrices with a 1 at the ij position. So, and then irreducible means that if you subtract a fraction of this type of matrix from your A, you're no longer in the copositive cone, you're somewhere on the boundary of the copositive cone. And then this set here, VA, those are the zeros of a matrix, so that means that U transpose AU is equal to 0. And then it just says that if your A is reducible in this direction, then there exists a type of 0 which has certain conditions, and that somehow at some point leads into this theorem, because apparently there's all kinds of properties that you can derive from a matrix based on what you know about their zeros, which just says that if you have some matrix here that satisfies this property, property 2.6, which is basically this, then either it's like a semi-definite matrix, or it's in the orbit of the Horn matrix, or it has these types of zeros. So the sub here means the support. And then again, Baumert goes for like 10 or 20 pages, goes through all of these cases for different types of zeros. And then you find that this guy actually means, I think it was semi-definite, and then here's something similar. So that's how eventually, well, you get to this result here. Like this, like these are the only options left, and it has to be these types of matrices. Okay, so again, to summarize, this is now the result that we have. If you have some matrix, then you can check whether it's in the copositive cone by checking whether the scaling, where the scaling is such that you get a binary diagonal is in K1, or alternatively, if you find this set B here as matrix with a binary diagonal, then the C5 or the copositive cone is still equal to the K1 in some sense, albeit intersected with some other set. So if you now recall the clique number, which was this here, so what the Clackham technique did in their paper was they just looked at some of these approximations for the KR. In particular, they looked at the K1 cone and noticed that for small examples this already worked quite well, and this gives some interpretation for that, at least for the 5 by 5 case, because on the diagonal here you have exactly the values lambda minus 1 everywhere, so it's like a constant diagonal. So in fact, for the 5 by 5 case, you get that these things are equal. Whether that's also true then for bigger cases, we don't really know. So that's like the question now. So can we do something similar where we so for any size matrix, can we find these scalings such as you get binary diagonal, and then would this then be a way to check whether your matrix is copositive or not? So again, for the clique number, there were some bounds found by de Klerk and Bonze. So if you lifted, I think it was alpha squared times, where alpha is the clique number, you'd get the exact answer. In fact, I've been working on graph isomorphism for a while now, and you can show similar results where these liftings are finite for getting or obtaining the exact answer. So this at least almost seems to point in the direction that maybe something like this is possible, albeit those things are both discrete in nature, so there's that. So I don't know if there's any continuous examples where these liftings are finite. And also the other way around, of course, which was pointed out to me by Monique Laurent. If something like this would hold true, for example, if this R would be some function of n, say n, it would also mean for the clique number that n liftings in fact would be enough to get the exact solution. So that was my dog.
Questions?
Can you go back to this slide where you proved the theorem about C5 involving this P of theta and this PSD plus non-negative? No, further back, please. Yes, here. So does this mean, so if I take a positive semi-definite matrix and I add some of these matrices S of theta, then I can express it as some non-negative matrix plus some permuted scaled version of another S of theta. That's strange, right?
Well, it's x not an S plus.
Huh?
But it's x not an S plus.
Sorry?
X is not PSD.
X is not PSD.
But
Not
if you
allowed to
add
be.
a S theta to
Yes, it might be.
Yeah, it might be.
Might be co-positive. It might.
No, but if I take a PSD matrix and I add a random S of theta, it will usually not be PSD, right?
Yeah, then
So I can apply the theorem,
Yeah.
and this seems very strange to me, but maybe it's true, I don't know. Maybe it's
Theorem is true, so.
So the theorem is correct.
Okay, this is the question, right? You should read the paper. Other questions, please?
So if instead of multiplying by sum of xi squared, if you allow yourself to multiply by, let's say, any quadratic, which you can search for, is there a 5 by 5 example where that fails?
So what exactly are we multiplying by xi squared?
So you have a quartic form that comes from copositivity, right? And to check whether it's non-negative, you can look for a quadratic polynomial such that the product is the sum of squares, but that quadratic can be anything. So I'm wondering if there is an example of a 5 by 5 matrix for which that fails.
Well, I wouldn't be able to tell you right now. I don't know.
You could do that scaling is equivalent to multiplying by a different quadratic.
Okay?
Well, so you're saying, so you're multiplying the order 4, the degree 4 bit with E transpose X.
Is
Yeah.
equivalent, so that would mean that for
The
5 by
scaling-
5, that would always work? There is a quadratic?
Yes, I believe so. The scaling is equivalent to take, well, you've basically got X transpose the identity matrix X, you're multiplying by, and the scaling is equivalent to replacing that identity matrix up in another process semi-definite. Like one matrix, then gosh, or diagonal matrix.
No, Carson?
So I mean, this result for 5 by 5 matrices with this scaling to the unit diagonal that's very nice. But, so is there any reason to think that that is, in general, a good thing to do? I mean, do you have any other, sort of any other machinery beyond that result for 5 by 5 matrices?
No, as far as I know, not really anything concrete now.
Other questions? Okay, let's thank the speaker again.